All right, hi everyone. We'll just give it another minute or so for people to continue logging in, and then we'll get started. All right, so that's 11:31 on my watch, so I say we get this going now. Since this is only meant to be 20 minutes plus questions, don't want to take too much of your time. So thanks everyone for tuning in. This is the first of a three-part series this week of webinars focused on the rail industry. Today is monitoring of tunnels, bridges, and structures. Just a quick logistics before we get into this. So we are live as we're doing this. My name is Chris Gerrans. I'm originally from New Brunswick, living now in Vancouver, and actually today I'm in Toronto. If I didn't have these beautiful curtains behind me, you'd be able to see the CN Tower. The rest of the team that are on the line here, we've got Dan Miller in New York and DJ Hogan in Chicago. They'll be on here answering questions. So if you're not used to this, which I assume most everyone on here is used to this by now, but on the right, there's a tab and there's a questions panel there. If you have any questions as we're going through this, please just fire those in, and Dan and DJ will get to them. And then there's a Q&A session at the end that will look at some of those questions. You can ask us more, and we'll try to answer everything. If we don't get to it today, I promise we get a log of all the questions, and we'll follow up after individually and take care of any of those. So why are we all here today? So I've got a quick animation showing what we're actually doing here. So this is what we're trying to do is mitigate risk. In tomorrow's webinar, you'll actually see a real life example of what this animation is based on. But this is what we're doing. We're trying to detect, notify things ahead of time so you can avoid any kind of disaster, which could have caused in this case. So how do we do that? With remote condition monitoring. That's what we specialize in. That's what we're here to learn about today. That's what I'm going to be presenting. So this is another kind of a picture of some examples of wireless remote condition monitoring. So what does that actually mean? So obviously wireless means no cables. There's nothing between the sensor and the data hub besides this wireless technology. Remote, you can be pretty much anywhere in the world. You don't need to send someone out there all the time. You can have live data. Condition is just obviously what that is, the status, performance, or behavior of whatever it is you're trying to monitor. And then again, monitoring, continually observing this over time so you can detect trends, notice if anything is moving. In this case, we've got pretty much everything here. We've got a rail going under in a tunnel. We've got sensors on the tunnel. We've got them on the earth. We've got them in the ground, piezometers, crack sensors, inclinometers, tilt sensors. The whole package can all be packaged up into one nice system. And again, what is the value of this? Well, you get near real-time data. You can get collection in the field. You can see it in the office within minutes of being collected if you choose to set up your data collection rate that fast. It works in all weather. You don't need to have someone out on site. If it's pouring rain or in the middle of nowhere, you can still see all of this, all the data from all of these instruments. You can get a real-life idea of what's happening to your structure. Again, we're all trying to just mitigate risk here. It's what we do. Early warnings, you can detect if there's any kind of trends in the data or movement, set those thresholds. Avoid costly manual monitoring. Again, if it's in a very remote site, you can set this up and get virtually data from anywhere in the world. And again, very easy to install. There's no cables. It can be solar paneled. You don't need to have mains there. Nice package all rolled up into one. And I'm just going to dive right into the wireless part of this first. So we offer two different platforms. We've got our flat mesh network, which is our mesh topology. So each node can also act as a repeater and send the data back to the gateway. It'll find automatically the strongest path to get the data back. If for some reason one of those paths is blocked for some reason, it'll find another route to make sure you're always getting data, and the nodes will talk to each other. And we've got a GEO1, which is our long range monitoring. This is a star topology. So all the data can be sent for very long distances, sometimes up to tens of kilometers, sent back to central gateway, and then all the data again sent back to the cloud to a web-based monitoring system. A little bit of what we do. So we've got on the left here is our triaxial tilt sensor nodes. This is most of our core business. So this will be used for structural movement, tunnel distortion, heave and settlement. There's a few different form factors. I'll dive into more of these later, but I just want to give an overview of them. We've got optical displacement sensor, which is essentially a triaxial tilt sensor with a built-in laser to give that distance measurement. We can use flexible inclinometers. This is a picture of a FlexiMeasure instrument here. Can incorporate other IPI systems into our system also. These can be used, again, for tunnel distortion, can be installed around the tunnel to detect changes in convergence, tunnel heave or settlement, structural movements, lateral distortion. And you can also integrate other sensors from third-party companies, such as piezometers, extensometers, crack sensors, MPBXs, external temperature sensor, pretty much the whole gamut of stuff can all be put into, again, one system. And this is how the whole thing kind of lays out as a whole. So on the left, we've got the sensors, the wireless telemetry, and all that data being sent remotely via the cloud into a secure server, and then available for analysis from the engineers in the office, yourselves likely, and that data can then also be viewed there or exported into virtually any third-party system. So this is the whole package as a whole, which we like to call wireless remote condition monitoring. So backing up a bit, wanted to introduce who Sensieve is. We're still relatively new to the North American market, so I wanted to quickly show who we are. We're a London-based company. That's where the headquarters is. We've been around for 16 years, since 2005. It was a spin out from the University College of London. And then we've got offices in 3 other locations. We've got London, we've got one in Perth, and the office in New York, and various people situated all throughout the globe. So we are a London-based, Canadian-owned, which offices all over the world. And as you can see, there's a few of us here in North America, so we've got most of the globe covered. And again, our core products are on the left. So this is what we're known for, is this wireless tilt sensing, ultra low powered, very reliable wireless systems. We've got our wireless tilt sensors, we've got cameras, the inclinometers, the ODS sensors. We can integrate other products into our package. We can even offer bespoke or custom solutions if needed. We've got the networks, which I already mentioned, and then we've got world-class top-rate support. So we've got a team, customer support team located all over the world to help address any issues that come up. I do see some questions coming in. Dan or DJ, if you need to cut me off with anything, just please let me know. And again, so our wireless technology, this is our wireless tilt sensors. We've got on the left, bottom left here is kind of the square standard triaxial tilt sensor. The other ones are our nano products. We've got the Nano Plus shown here. Same technology, slightly different form factor, and the main difference is just the battery life between them. They all are incredibly reliable, incredibly accurate, but just different form factors, different ways of installing them. We've got magnets, structural brackets. Some of them can be glued in place. It all depends on the specific application and what you need them for. You can take that same triaxial tilt sensor and add a distance laser measurement. So what you can do with this, in the top left, this is inside a tunnel arch where you can actually measure the lateral distance along with the 3-dimensional tilt. So you get those tilt readings plus a distance measurement. So it's a very powerful tool to be able to determine what's happening with structures like this. And I'll actually show a case study later of that top picture where they actually use these sensors to determine the lengths and come up with the chords of that tunnel. Same triaxial tilt sensors can also be used in our inclinometer. This is our FlexiMeasure. It's available in 4 different segment lengths. It's essentially a flexible inclinometer is how we call it. So it can come in lengths of 0.5 meter, 1 meter, 2 meter, 3 meter lengths, easy to connect. You can put these on the side of a structure, along the top of a tunnel to measure the heave, even around the inside of the tunnel to measure changes in convergence. I'm just assuming everyone can see my hands. Very reliable, connects into a data logger, and all the data goes back into the same system that you'd see with all the other ones. So you can incorporate this inclinometer into the same online portfolio that you can see with all the other products. And as mentioned before, you can integrate third-party sensors into this. So you can put a piezometer, a crack sensor, a temperature sensor. All of these things can be connected into the same wireless system, and then you can access all of this data in real time remotely, along with the data from all of our instruments. You can get them from other instruments too. If you have a question about a specific sensor, please just let us know. We've either already incorporated it, or it's something we can look into incorporating into our system, but just please let us know, and we'll get back to you. We also have a camera technology, which can still be built into the same system. You can actually set these up to be automated. They can be triggered by movements if you choose. They're very high accurate. They work all day, as you can see, either midday, at night, to get a really good visual representation of what's happening on the site. And a little more information on our flat mesh network itself. As I mentioned, this one is more for more condensed sensor networks, usually just a few hundred meters max between all of the sensors, maximum 2K with 32 max hops between all of the nodes back to the gateway. Very powerful, really what we're known for. It's a great package. You can see on the bottom here the different typical sensor spacing that we use depending on the application. And then in contrast to that, we've got our GeoWAN network, which is our long-range system star topology. So the sensors don't talk to one another; they all talk directly back to the gateway. But the benefit of this is that you can get very long readings. You can get up to 15 kilometers line of sight between the sensor node and the gateway itself. And again, down at the right, you can see the different environment and the different ranges that we've observed in the real world with this sort of stuff. Excuse me. Perfect. And then what good is all of this if you can't see it online? So our platform is called Web Monitor. This is where all of the data from all of these sensors and all of these integration nodes that I've been showing all come. So this is where you can configure your system. You can see the live data. You can check on the status of the batteries, the strength of your network. You can maybe detect ahead of time if you need to switch something around, if you need to send someone up to site to take a look, whatever it is. You can do all of this right from Web Monitor. It's very powerful. We'll help you set all this up. We can show you exactly what you need to do, and then it's all there. And the other thing, you can actually export it from Web Monitor into virtually any other third-party cloud-based system out there, or you can even just download it, put it into Excel, whatever you're used to doing. We're flexible. You don't need to use this, but it's there for you. Now that I've shown a little bit about who we are, all of the technology, show you some real world pictures of how this can be used, and hopefully trigger some ideas in your mind about how you can use this on your own projects. And I'm hoping that at the end of this, we'll have some good Q&A sessions, or we can set up meetings with any of you personally to talk about your projects and see how we can use our technology for you. So this is a case where it's a long rail bridge. As you can see, a new bridge is being built very close to it. So in order to monitor that they didn't do any damage to the existing bridge, they installed a whole bunch of our triaxial tilt sensors along the bridge itself. You can see them here circled, or I guess highlighted, right on the sleeper or the ties. And again, those are all talking to one another and then all communicating back to a gateway so they can check the data in real time. Another example, this one uses the ODS, or the optical displacement sensor I mentioned. It's triaxial tilt sensors with a built-in laser distance measurement. And in this case, the sensors themselves are the squares, and the dotted lines are obviously the distance measurement that they are measuring. So they're shooting from the crown of the tunnel or the arch out to the sides to measure that distance to ensure nothing was even moving or tilting at the top, and they wanted to know if it was moving laterally at the same time. Again, another picture of using the ODS. This is under obviously a road, and they're wondering how the columns and the pillars are moving both laterally and and checking if they're moving, if they're tilting themselves. So they wanted to know both lateral movement and the tilt. Some more triaxial tilt sensors on a bridge. This is a rail bridge, as you can see. They've got them both on the columns themselves and on the bridge to measure any of those movements. Again, all talking to one another, all seen in real time, any notifications if anything starts to adjust. Inside a tunnel, this is the one I was mentioning earlier, where these are using the ODS again, the tilt sensors, and you can see on the left where they've installed multiple ODSs around the tunnel itself, and they've set up the lasers to measure to a target here, and then they can calculate those chord lengths. And then if anything starts to move laterally, they also have the tilt measurements from each of those individual ODSs to know, they can know exactly what's happening within that tunnel. And they can put a series of these all along the tunnel so they get a complete picture of how it's behaving. Another example, this is actually a dam, obviously, as you can see, but this is a good example of how discrete the nano sensors are themselves. You can hardly see them on the left, and even if you're up close, it's hard to picture them. But in this case, it's they wanted to know what was happening now. You could even detect this when the water goes up and down, if they were doing construction on site. You can even pick up seasonal trends as it moves with either the tides, the water levels, even the weather. It's pretty powerful. You can put these same, these same sensors, either the nano tilt sensors or the standard IX tilt sensors attached to a beam to create what we call tilt beams. So you can put these on a structure to get an exact idea of how it's moving. So say you didn't know exactly where it was going to move, you can put one of these beams on there and it'll actually pick up any of that movement, and you can tie these all together to create a nice chain of sensors and measurements. So you get a complete profile. The top picture there measuring any settlement or heave, and on the right, it's mounted vertically, so they'll pick up any lateral movement of that structure. Another example of this is on the face of a dam. They use the nano sensors again here, and you can see these are going all the way up the face of the dam, so they'll get any kind of movements of that structure. And again, all these are, again, wireless, they're all talking to one another, so you can get a complete wireless real-time idea of what's happening with this project. And the fleximeasure. This one, as I mentioned earlier, can be installed on the face of structures to measure any lateral movement. It's available in different segment lengths from 0.5 meter up to 3 meter, all easily connected in the field, completely waterproof. These connect directly back into a Edge Hub data logger. That's what's shown on the bottom right here. In this case, it's on obviously a wall, but you can also mount this structurally on the top of a tunnel to measure any settlement or heave. It can go around the inside of a tunnel to measure convergence or divergence, or along a bridge if you wanted to measure settlement that way, or on pillars, anything like that where you need either lateral or vertical settlement or heave detection. So thank you very much. That was a lot of information squeezed into not a lot of time. I know everyone's busy, so I haven't seen if any questions have rolled in. Hopefully there is some. Dan, DJ,
Yep.
Anything we need to go over? Perfect.
Yeah, we do have some questions that have rolled in during this, so I'll run through them. And if anyone else has any questions, as they're absorbing this information that Chris just went through, feel free to throw them in as I'm running through. So the first one here is the long range network using the LoRa network. So yes, that is correct. So there's our two platforms, as Chris covered, one being the flat mesh, the second being GeoWAN. Our GeoWAN platform runs on in North America, the 915 megahertz LoRaWAN based frequency. So yes.
Thanks, Dan.
Next question, unless someone wants to jump in. What do you offer to monitor the envelope of a tunnel? So we want to take that?
Yeah, so was that, I'm curious as to when that came in. Was it before I showed the examples or after? But yeah, so we've got the multiple options to measure in tunnels. We've got, you can use the ODS, the tilt sensors, you can even create tilt beams or flexi measure, in addition to all the other kind of tilt sensor, or sorry, external sensors, like we've got the extensometers, crack sensors, temperature sensors, whatever the application, just let us know. We can chat about it. Is there anything in addition to that, Dan, that I missed?
Nope. Sounds good. I'll keep running through these here. I think we've got about 10 minutes left, so
Oh yeah, no
we
rush.
should be good.
Hey,
Rails
Chris, what options do we have like inside a tunnel, where you may not have cellular coverage?
Yeah, we do have some options. It's best, we can sometimes we can put a kind of a USB hub there. We can hook up Ethernet. It's kind of site specific depending on what is available at that project. So we have done multiple projects inside tunnels and have been able to get the data out. Sometimes you can run either long antennas or long cables and then put a cell modem. We prefer not to do that, but sometimes there's no other option.
Okay, thanks. Going through here. Rail is a very tough environment. What have Sensieve done over the years to make sure the equipment is fit for purpose? I'll take that one.
I was gonna say, that's a good teaser into your webinar in 2 days from now, right, Dan?
On Thursday, that's right. A good plug for me, thank you. So our nodes that are designed for rail environments, specifically track bed, they are designed specifically for the harsh conditions of track bed. So that includes weatherproofing. So we have IP66, 67, and 68 weatherproof rating on all nodes that are installed on track bed. Enclosures are high impact design, designed to take the impact of, a chain, for example, that could be hanging from a train and getting hit. We have plenty of case examples of these things being struck. Additionally, and what's unique to Sensieve is our tilt sensors have a high G variant, which make them able to survive, high levels of vibration on track bed that you can experience on ties. So for high-speed rail, or really just on bridges, rail bridges, or just areas where ties seem to shift around a lot, we have that high G variant of our tilt sensor for track bed.
Yeah, that's a great point.
Running through here, next one, how should I choose flat mesh or GeoWAN, and what are the strengths and limitations of both?
Perfect. Yeah, do you want to take that, Dan, or do you want me to go for it?
Sure, yeah, no, I'll hop in. So basically, Chris did cover this between flat mesh and GeoWAN, but essentially, flat mesh has some unique properties that allow it to do some things that basic LoRa networks can't accomplish. Flat mesh is a proprietary network unique to Sensieve, allows high reporting frequency on our platform, allows us to get down to 2-second monitoring frequency on certain nodes. It allows some automatic triggering and some smart processing locally on site. Doesn't require us to have processing done in the cloud. We can react on site. So really it comes down to the project. Are we looking at a dense sensor cluster like Chris mentioned with high frequency reporting, or are we looking for more of a long range, more passive monitoring regime? So again, like Chris mentioned during the presentation, we always look at these, or our partners or distributors always look at these different cases and recommend a certain platform for a specific application.
Yeah, exactly. They all have unique features, and it kind of comes down to a case by case, project by project, whatever one works best for you. And the good thing is you can even set up both systems on one site if you want. They won't talk to one another, but all the data will show up in the same system and will look identical. So that's pretty nice.
Yep. All right, we got another one here. How does the North American railroads monitor these issues at the moment if Sensieve are relatively new to the market? How is the uptake of the Sensieve solution by the Class 1s? Do they see the Sensieve solutions as an improvement on the existing techniques? This is a good one. This is a loaded one. I'll jump in on here. Yeah, so yeah, I mean, I guess if we're looking at railroads specifically, we're looking at track bed, we're looking at railroad bridges. all of these things, of course, have been monitored for movement outside, set tolerances that the FRA or specific railroads or REMA have set more traditionally. The most common way is a survey team going around and taking, elevation readings. You can go more traditional with a gauge bar, walking along the rail and, putting the gauge bar at certain locations to see if it's out of tolerance. And then there's newer technology like, trolleys with scanning technology. There's all sorts of, different technology on the market. What's unique to Sensieve and Sensieve's offering to rail is low power, long life, early warning on track movement, track geometry movement, settlement, etc. So this is something that we are busy introducing to the market, to the class ones. Have very good reception thus far. So yeah, looking forward to working more with the market and anyone else who may be on here without revealing too much about what we're up to. Got one more I'll jump in on here before we're getting close. So what sort of accuracy are you getting on the laser distance monitoring, and what sort of distances can be monitored? So the accuracy, so on our ODS sensor, the laser module that we use is a class 2 laser. So it's very similar to a total station. What we accomplish with that up to 150 meters, which is our range, is going to be plus or minus 0.15 millimeter. So it's a highly precise and repeatable measurement that we're accomplishing with the ODS. So it can be used, with a lot of confidence in the case of, for example, what was discussed earlier is tunnel envelope. So the combination of the ODS having that laser module, that distance measurement, and the ability to detect tilt helps our customers and users really understand, how that tunnel is behaving and how it's changing by change of distance, by the tilt at the node, so how the wall is reacting. It allows us to do some very, precise convergence type measurements, and that's what you use, of course, when you're looking for tunnel envelope changes.
Yeah, thanks, Dan.
Thank you.
Cool. Anything else?
No, I think that we're good there. So I didn't see any more come in. So probably good to wrap it if you guys are all set.
Awesome. Yeah, thanks everyone for tuning in. Again, this was the first of 3. Tomorrow, Simon will be going over specific case studies around earthworks, and then again, Dan will be presenting Thursday more track-specific application and projects and technologies. Again, if you have any questions, please don't hesitate to reach out. We will reach out to you and answer those questions we may not have got to. If you have anything else, please just let us know. We're here to help. Anything else, Dan or DJ?
All set.
Great. Thanks, everybody.
Bye, everyone.
Thanks, everyone.